Think about temperature or mass. If I tell you that outside there's a temperature of 25 degrees, that's enough information for you. If I tell you that I need to send a package, a box, and the company charged me by the weight, and I tell you that my box weighs 10 kilograms, that's all the information that you need, right? These type of numbers are called scalars. These are called scalars. These are quantities that are defined strictly by their magnitude or their size. Okay, but the real world isn't that simple. Imagine that your car, the car in which you're traveling, broke down. So you have a car, you're traveling on your car, and suddenly it broke down. Okay, and you gotta push it. You gotta push it to the near gas station. So to push it, you know that you need to apply a force, right? But if you analyze it, if you push it uphill in this direction, it's going to be different that if you push it sideways, right? If you push it sideways, you will just hit the curb. If you push it back, then it's easier, right? Because it's flat ground. But if you push it up in this direction, it's going to be hard, right? You need to apply more force. So in this case, the direction matters just as much as the strength. Since this is different than the previous, than the box and the temperature, because it's different because we have a direction and a force and a strength. So this situation needs a better tool, a better mathematical tool to explain it. And that's what we call vectors. In this video, the ideas that we learn about vectors, their notation, and how they work and what they are, the language of motion and force. A vector, it's geometrically has an initial point, let's call it A, and an end point, let's call it V. Okay? The line segment that goes in this direction, it's called a vector. And their notation, this can be the vector V, so we call it vector V, or we can call it vector AB. Okay? This states the initial point and the terminal point. So this is the initial point, and this is the terminal point. Vectors can be equal to other vectors. For example, if I roughly draw vectors of the same magnitude, the same length, and the same direction, we say that these vectors are equal. Okay? Also, if one vector, let's call vector AB here, it's followed by another vector VC, there is a resultant vector in between these two, that's the vector AC. Okay, so in other words, vector AB added to vector VC, it's equal to this new vector AC. Okay, usually we use a simple notation for this. If we have vector U followed by vector V, then we have the resultant vector U plus V. If we have two vectors with the same initial point, this is vector U, this is vector V, okay? The sum of these two vectors, the resultant vector, is going to be the diagonal of the parallelogram that we can form here. So this green vector is going to be U plus V. And that's how we define the sum of vectors. What happens if maybe we have a vector going up like this, right? And maybe another vector going back like this. All right? That will be a negative vector, right? And the diagonal of this parallelogram is going to be defined by u plus negative b. That means u minus b. Okay? So that's how we can define the subtraction of vectors. Okay? If you notice, this will be our positive or addition, u plus b, and the green one will be our subtraction. Let's move vectors to the coordinate plane. If we have the coordinate plane, and now we have this initial point, this will be x1. Let's call it x1, and this will be y1. So this will be the coordinate or the point x1, y1, right? If I have a terminal point here, and I just draw my vector, okay, this will be x2, and this will be y2. So this point is the coordinate, is defined by the coordinate x2, y2. Okay? If a vector is represented in the coordinate plane like this, with an initial point x1, y1, and a terminal point x2, y2, then we can define the vector as, and we're going to use this brackets, this type of bracket, x2 minus x1 and y2 minus y1. Okay, so what this is saying is that this will represent a vector in the coordinate plane. Also, this way of writing a vector is called the component form of a vector. Okay? Now, let's do an example. Let's find the component form of a vector v, which initial point it's -3, 4, and the terminal point, so initial point and terminal point, it's 4, 6. Okay? Following the component form, we know that vector v is going to be equal to 4 minus 3, so 4 minus 3, and 6 minus 4. 6 minus 4. 4 minus 3 will be positive 3, so 4 plus 3 will be 7. And 6 minus 4 will be 2. So the component form of a vector that starts at -3, 4 and ends at 4, 6 is this. How this vector looks in the coordinate plane. So if this is 1, 2, 3, this is 1, 2, 3, 4, this is my initial point. The terminal point is 4, 6. So if this is 1, 2, 3, 4, this will be 4, 5, 6. This will be my terminal point. So that is my vector. Okay? And I can represent it in this way as the component form. The horizontal, what we are going to call the horizontal component and the vertical component. Usually, the notation that we use is going to be Bx and By. And let me use a different color. By. Okay. The vertical component comes from the displacement that we got vertically. The horizontal component comes from the displacement that we got horizontally. If you notice, from this initial point horizontally, we need to move 7 units to the right. 1 unit, 2 units, 3, 4, 5, 6, and 7 units. Okay? That is our horizontal component. And to reach our terminal point, we need to go up 2 units. 1 and 2. 2 units. And that's what we got here. Our vertical component called By, it's the number of units that we move up, is pretty similar of what you know as the rise when you study slopes. And the horizontal component, it's what you move horizontally, are pretty much the same thing that you know as the run when we studied slopes. Now, let's do a different example. Let's suppose that we have a vector 3, 7 in component form. And the initial point, it's 2, 4. 2, 4. What will be our terminal point? Okay, so let's assign variables to our terminal point. This is x and y. We know that if we subtract these two quantities, x minus 2, we will get the horizontal component that is 3, right? So if we just solve this small equation and we add 2 on both sides, 3 plus 2 will be 5. So we know that the x coordinate for the terminal point will be 5. The same goes with y. We know that the vertical component is the result of subtracting these two coordinates. So y minus 4 must be equal to 7. And we can solve this equation fairly easy. Plus 4 plus 4. This is gone. 7 plus 4, it's 11. So y is equal to 11. So now we find that the terminal point must be 5 and 11. We can check if this is true really easily. 5 minus 2 is 3, 11 minus 4 is 7. So for this initial point, in this vector, the terminal point must be 5 and 11. If you remember from the start, vectors not only has direction, they also have magnitude. So if we have the vector in component form AB, basically what we have is a vector in which the horizontal component is going to be A units and the vertical component is going to be B units, right? In other words, if we had a vector 2, 5, the horizontal component will be 2 and the vertical component will be 5. This is a right triangle. And in a right triangle, if we know the sides by the Pythagorean theorem, we can find the hypotenuse. And the magnitude in this case of the vector is going to be the hypotenuse of the right triangle. That will be their size, their length. Okay? So we can use that result to find the magnitude of a vector. So the magnitude of a vector will be represented by this symbol, 2 bars. Sometimes 1 bar it's enough, but can be confused with absolute value. So it's really common that we use 2 bars. B will be equal to the square root of a squared plus b squared. Notice that in this case, the magnitude of the vector represented by this symbol, magnitude of a vector, it's the hypotenuse of the right triangle. And what we have here is the Pythagorean theorem isolating already the hypotenuse. Let's do one example. Let's suppose that we have vector u with components 2 and -3. What will be the magnitude of this vector? So the magnitude of this vector will be magnitude of u will be the square root of horizontal component or component x, 2 to the power of 2, plus the vertical component squared, so -3 squared. 2 squared is 4. -3 to the power of 2 is 9. This will be 13. So the magnitude of the vector u is going to be 13, square root of 13. Let's do one more. What about the magnitude of vector -5, 0? The magnitude of this vector will be the square root of the square of the horizontal component, or the x component, plus y component squared. 5 squared is 25. 0 squared is 0. This will be 25, square root of 25. That is 5. So the magnitude of vector v will be 5. Okay? Let's do one last example. Let's suppose that we have vector m with components 3/5 and 4/5. Okay, we do the same thing. Magnitude of m will be equal to the square root of 3/5 squared plus 4/5 squared. 3 squared is 9, 5 squared is 25, plus 4 squared is 16, 5 squared is 25. These are like fractions, so we can add them. 9 plus 16 is 25/25, and this is 1. So the magnitude of m will be square root of 1, and the square root of 1 will be 1. Okay? So the magnitude of vector m will be 1. When the magnitude of a vector is 1, it's going to be called a unit vector. A unit vector. Because its magnitude is 1. The most simple unit vectors are the vectors I, 1, 0, and the vector j, 0, 1. If you have the coordinate plane, I will be this vector, right? Because the horizontal component is 1 and the vertical component is 0, so it doesn't go up. This is I vector. And j vector is going to be 0, 1. So if this is 1 for the vertical component, then we must go up 1 unit, and we do not move horizontally because the displacement is 0. Horizontal component is 0. So those are the basic unit vectors. Any vector v in the component form can be expressed in terms of I and j. How? Vector AB can be expressed as AI. So the horizontal component is going to be multiplied by the I vector, that is the horizontal, this horizontal vector right here, plus V times the j vector. V times j vector. So in this way, we can express any vector this way. Let's do an example. Let's suppose that we have vector -2, 3. How can we rewrite this vector in this form? Well, the only thing that we need to do is take this horizontal component -2 and multiply by the I vector and add it to the vertical component multiply by the j vector. And this will be the vector represented in terms of I and j. Let's do another example. Let's write vector u with components 5, -2 in terms of the unit vectors I and j. And so the only thing that we need to do is take the horizontal component 5 or multiply it by I, and then add it by the vertical component -2 that is multiplied by j. Positive times a negative is negative, so we know that the vector u can be written in terms of the unit vectors as 5i minus 2j. So let's suppose that we have a vector with an initial point in the origin, and that we have a direction theta. So we're going on that way. We're going that way, okay? This is the direction of our vector. If our vector in component form is AB, we know that the horizontal component, it's A, and our vertical component, it's B. And again, we have a right triangle. Since we have a right triangle and a direction given as theta, we know that we can find each of this component given the direction and the magnitude of the vector. Notice that we can use the trigonometric ratios to find the components, the vertical and the horizontal component. Remember that this is their magnitude. So let's call this magnitude V. We can relate these quantities using trigonometric ratios. For example, cosine of theta is going to be equal to adjacent, that is A, over hypotenuse, that is the magnitude of B, of the vector. If we isolate for A, we get that A is equal to the magnitude V times cosine of theta. So if we have the magnitude of the vector and theta, we can find the component A. The same goes with B. Sine of theta relates the opposite and the magnitude, and the hypotenuse, that in this case is the magnitude. So V over magnitude V. So if we isolate V, we get that V is equal to magnitude of the vector times sine of theta. And now we have two formulas that are really useful to find the vector given the magnitude and the direction. Let's look at an example. Let's suppose that we have a vector with magnitude 4. And the direction of the vector, it's pi over 4. Okay? So we can find the vector using these two formulas. So if you remember from just 1 minute ago, we can find the horizontal component with 4, the magnitude, multiplied by cosine of pi over 4. Remember, A can be found by multiplying the magnitude times cosine of theta, and B can be found multiplying the magnitude times sine of theta. So this is our horizontal component, and we can find the vertical component by multiplying 4 times sine of pi over 4, right? We know that pi over 4 is basically 45 degrees. And we have a triangle, a special triangle, in which these are 1s and this is square root of 2. So cosine will be 1 over square root of 2, that is square root of 2 over 2. So 4 times square root of 2 over 2. And sine of pi over 4 will be opposite over hypotenuse, 1 over square root of 2. This is exactly the same as square root of 2 over 2. Okay, we can simplify this. 4 divided by 2 is 2. 4 divided by 2 is 2. So our vector is going to be equal to 2 square root of 2 and 2 square root of 2. This is our component form of our vector given this direction and its magnitude. Okay, in the next video, we're going to learn about operations of vectors and how to solve problems related to them.